Lab 5, the physics of the home run. In 2021, Jorge Soler of the Atlanta Braves hit a towering home run to clinch the World Series. The ball was hit so far, the camera could not see where it landed after it left the stadium. While rumors say the ball is still in orbit around the Earth, the purpose of this lab is to calculate where it actually landed. The distance the ball traveled can be interpreted as a displacement in the x direction. After that was approximated, using the formula for impulse, the amount of force Jorge Soler applied to the ball was also approximated. The system in this lab is the ball, and the surroundings is just the Earth. The ball traveled 200.13 meters, and the force applied was 232 newtons. All data is based on Baseball Savant's recording of MLB's StatCast system. The initial position of the baseball was 0.7780, and the initial velocity was 49.04 meters per second. Breaking that down into the component form, the initial velocity was 43.69 meters per second in the x direction and 22.26 in the y direction. And the ball was hit with a launch angle of 26 degrees from the horizontal. Some relevant formulas are the time until the peak of the ascent of the ball, which states that the initial velocity divided by the little g, 9.8, is the time it takes to reach its apex. The max height is then negative half g times t squared plus the initial velocity times the time plus the initial height, where t is t max. Time from peak until the ground can be understood as just a free fall, y max minus half g squared. All of those kinematic equations were derived from calculus. The position and velocity update formulas, and the formula for impulse, which states that the change in momentum is equal to the force times the change in time. A walkthrough of the computational model. First, the initial conditions of the system is set, like the initial position and velocity of the ball, as well as its mass and the timestamp. And then calculating the amount of time until the ball reaches its apex. And once we have that, we can iterate with a while loop while t is less than time max. And in this while loop, the initial velocity, once it's hit off the bat, is considered in tracking its location. And it is a while loop that iterates with every 0.033 seconds it adds to the graph. And then the second while loop starts with the apex point, and there is no more initial velocity, as the velocity at the apex is 0. So it's just a free fall of sorts where the ball falls from the top of its peak to the floor. And here you can see setting the initial systems of the condition, or the initial conditions of the system, and calculating the max height, the time toward the max height, and the total amount of time the ball is in the air. And then we can make our while loops where we update the position and velocity, or position in the x and y directions of the ball while t is less than t max. Once t gets to t max, the velocity of the ball at the apex is 0, so we reset that and we do it again where we update the position and velocity in each direction while moving the clock up the timestamps. Here are the results of the lab. We can see that the ball traveled about 200 meters and it was in the air for about 4.7 seconds. And it reached a maximum height of about 27 meters above the ground. Here we can see another set of graphs, and this is actually where there's a giant train track in the left field fence of the Houston Astros Stadium, where once the ball clears that train track, you can't see it again. So here's where it is about 27 meters above the ground, and it clears that wall, which is about 100 meters deep, so we can't really see that at all, but it's pretty cool that it travels about 100 more meters after the camera even sees it. So it was a pretty big home run. One problem with this computational model is that it does neglect the effect of air resistance, so that would cause the ball to travel shorter than what the model projects, but this model was built by me, and it took a long time, so this is all we could do for this lab, but further exploration would improve that by creating a model that accounts for air resistance. Now, how much force did Jorge Soler apply? Well, in order to use the impulse formula, we need the amount of time that the ball was in contact with the bat, and we can approximate this by knowing that the MLB broadcast uses a camera that shoots 60 frames per second, and the ball was in the frame, with the bat for 1 second. So delta t is about 1/60th, or 0.0167 seconds. The velocity of the pitch was 37.3 meters per second in the opposite direction, and the mass of the ball was 0.045 kilograms. So using that impulse formula, we could find the difference in the velocities and multiply that by the mass and divide it by the amount of time to get the force of 232.9 newtons. So strong man in order to hit the ball with 232.9 newtons of force.